Welcome to chapter 16 on signed addition. In this chapter we will deal with the following questions. How are signed integers represented in a computer? By signed integers we mean integers that are either positive or negative, they have a sign. Second question, how are signed integers added and subtracted in a computer? Third question is whether we can use the same circuitry for adding unsigned and signed integers. By unsigned integers, I mean integers that are represented in binary representation. Finally, we will address the question is what is the purpose of the carry and input C0 in binary adders? Recall that in the binary adder we have the two addends A and B and the carry in C0. What is the role of this C0? Why do we have it? If we think about the purpose of such a circuit, it's supposed to support addition in programming languages, and I'm not aware of any programming language in which you have an instruction add A plus B plus a single bit. So why do we have this single bit in our hardware if no programming language can benefit from it? How do we represent negative numbers in using binary strings? There are three main suggestions. The first suggestion is to use sign magnitude representation. The second one is one's complement, and the third one is two's complement. In sign magnitude representation, the integer is represented by a binary string and the sign bit. Now recall that minus 1 to the power of 0 is 1 and minus 1 to the power of minus 1 is minus 1. So the number that is represented by the string A and the sign bit S is defined by minus 1 to the power of S times the number represented by A in binary representation. So you can think of this portion as the absolute value of the number and as this portion as the sign, which either equals 1 or minus 1, plus or minus. In one's complement representation, we take a binary string n and we partition it into the first n minus 1 bits and the most significant bit. The first n minus 1 bits represent a number in binary representation. The most significant bit has a very strange weight. Its weight is minus 2 to the power of n minus 1 minus 1. In two's complement, we have a very similar situation to the one in one's complement, but here the weight of the most significant bit is minus 2 to the power of n minus 1. Let's see some examples. Here we consider binary strings of length 3, and we consider the number represented by these binary strings in binary representation, the number represented by these strings in two's complement, in one's complement, and in sign magnitude representation. Let's start with sign magnitude representation. We have the leading bit here, which is the sign bit. It could be either a 0 or 1. If it's a 0, the sign of the number is a plus. If it's a 1, the sign of the number is a minus. The remaining two bits represent the absolute value of the number. So it's 0, 1, 2, 3, 0, 1, 2, 3. This explains the sign magnitude representation. Let's talk about the two's complement representation. In two's complement representation, with 3 bits, the number which is represented by these binary strings is minus 2 to the power of 2, which is 4, times A2, plus the number represented by the remaining 2 bits in binary representation. So, if this most significant bit is 0, then the first addend is 0, and we're left with the remaining 2 bits, which represent 0, 1, 2, 3, and we are identical with the case in which we're looking at binary representation. What happens if the most significant bit is 1? Well, if the most significant bit is 1, its weight is minus 4, so we have here minus 4 minus 0, minus 4 plus 0, it's a minus 4, minus 4 plus 1, it's a minus 3, minus 4 plus 2, it's a minus 2, minus 4 plus 3, it's a minus 1. So you see that in two's complement representation, each value is uniquely represented by a binary string. In sign magnitude, 0 has two representations. There's the plus 0 and the minus 0. So we have two representations for 0. Let's talk about 1's complement representation. Recall that in 1's complement representation, the weight of A2 is minus 2 to the power of 2 minus 1, which is minus 3. So if the most significant bit is 0, then this part becomes 0. We're left with this part, and it's identical to what we have in 2's complement, which is identical to what we have in binary. So all three representations agree in these four cases. Now let's consider the most significant bit being equal to 1. Its weight is minus 3, so we have minus 3 plus 0, it's minus 3, minus 3 plus 1, it's minus 2, minus 3 plus 2 is minus 1, and minus 3 plus 3 gives us 0. We notice that in 1's complement, 0 has two representations. One is the all 0 string, and the other one is the all 1 string. Okay? Notice that the range in the sign magnitude and 1's complement representation is symmetric. It's from minus 3 to 3. And here it is from minus 3 to 3. However, in 2's complement representation, the range is not symmetric. The smallest number we can represent is minus 4. The largest number is 3. Notice also that in 1's complement and in sign magnitude, we have two representations for 0. Why is unique representation so important? Consider a statement in your favorite programming language, which compares two variables a and b and says, well, if a equals b, then do something. How do you compare a and b? Well, if you have unique representation, then you can compare a and b by comparing their bits pair by pair. Now, if you were to use 1's complement representation, and a and b were the all 0 strings and the all 1 strings, they disagree on all bits, yet they represent the same number. So comparison becomes a little bit more complicated if you do not have unique representation. So this we have here, again, the definition of 2's complement representation. Let us denote by Tn the set of integers that are representable in 2's complement representation using n bits, and similarly let Bn denote the set of integers that are representable in binary representation using n bits. So Bn, we already know, is 0 to 2 to the power of n minus 1. Tn, on the other hand, you can check, it's from minus 2 to the power of n minus 1. This is the case in which this bit is 1 and all these bits are 0. Up to 2 to the power of n minus 1 minus 1. This is the case in which all these bits are 1 and this bit is 0. So this is the largest number that is representable in 2's complement representation using n bits, and this is the smallest number. So for example, for n equals 3, B3 is the interval from 0 to 7, and Tn, T3, it should be a 3, and T3 is from minus 4 to 3, as we already saw. Now consider a string A of n bits, and now we can interpret the string in two ways. One, we can interpret it as if it's representing a number in binary representation, or as if it's representing a number in 2's complement representation. What is the relation between these two numbers? Well, if the most significant bit of A is 0, then they represent the same number. We saw that in our example. But if the most significant bit is 1, we claim that the number represented by A in 2's complement representation equals the number represented by A in binary representation minus 2 to the power of n. Before we prove this claim, let's see an example. Consider n equals 4 and the string A, which is 0, 1, 1, 0. So the leading bit is 0, and therefore the string represents the same number 6, both in binary representation and 2's complement representation. Let's look at B. The leading bit is 1. So, according to our claim, there should be a difference of 16 between the number represented by B in binary representation and in 2's complement representation. Indeed, the number represented by B is 9 in binary representation, and in 2's complement representation, this bit has a weight of minus 8, and this bit contributes a 1, so we have minus 8 plus 1, that's minus 7, and indeed the difference, minus 7, is 9 minus 16, as the claim suggests. So let's prove the claim. Recall, this is the definition of 2's complement representation. Let's consider two cases: that the most significant bit is 0 and that the most significant bit is 1. If the most significant bit is 0, then the term corresponding to a in minus 1 is 0, and we're left with this part. So the number represented by a in 2's complement equals the number represented by the bits of a from position n minus 2 to 0. We can add a leading 0 if we wish, and that will give us the number represented by a in binary representation. Now let's assume that the most significant bit is 1. The most significant bit is 1, and this part contributes minus 2 to the power of n minus 1. So this is what we get over here. And now we can write minus 2 to the power of n minus 1 is the difference between minus 2 to the n plus 2 to the n minus 1. Now, this part over here is just the number represented by 1 concatenated with a from position n minus 1 to 2. And this bit, the 1, equals a n minus 1. So what we have over here is simply the number represented by the bits of a from position n minus 1 to 0 in binary representation minus 2 to the power of n. And this completes the proof, because the number represented by a in 2's complement representation equals the number represented by a in binary representation minus 2 to the n if the most significant bit is 1. Okay, so we have an alternative definition of 2's complement representation based on the most significant bit. As a result, we see immediately that for every binary string, either the number represented by a in binary representation and the number represented by a in 2's complement representation are the same, or their difference is 2 to the n, namely the number represented by a in binary and the number represented by a in 2's complement have the same remainder when divided by 2 to the n. Consider the problem that you're given x and you want to find a binary string of n bits such that the number represented by a in 2's complement representation equals x. So here we present an algorithm that solves this problem. If x is not representable by n bits in 2's complement, then we return fail. If x is not negative, we return 0 concatenated with n minus 1 bits that represent x in binary representation. If x is negative, we return the binary representation of x plus 2 to the n using n bits. We claim that the algorithm outputs the correct a if x isn't the n. Okay, so we need to consider two cases. Either x is not negative or x is negative. If x is not negative, then the number represented by the output of the algorithm in 2's complement representation, where in this case, is the number represented by a in binary, because the most significant bit is 0. And the number represented by a in binary is x by definition. So we get the x over here. If x is negative, then we look at the x plus 2 to the n. X plus 2 to the n cannot be less than 2 to the power of n minus 1, because x is in Tn, so the smallest value that it could have is minus 2 to the power of n minus 1. Therefore, the most significant bit of a, this is the binary representation of x plus 2 to the n, has to be 1. But if the most significant bit of a is 1, then the number represented by a in 2's complement representation equals the number represented by a in binary minus 2 to the n. Now, the number represented by a in binary representation, by definition, is x plus 2 to the n. So we have plus 2 to the n minus 2 to the n. We're left with the x, and that completes the proof. Let's see a few examples of computing the 2's complement representation of a number. You consider the case in which n equals 4, so we know that t4 is from minus 8 to plus 7. We want to compute the 2's complement representation of 8 using 4 bits. Well, 8 is too big, it's out of range. Therefore, we return fail. We want to compute the 2's complement representation of 5. Well, 5 is positive, so it is the 0 concatenated with the representation of 5, so it's 0, 1, 0, 1. We want to compute the 2's complement representation of minus 6. Minus 6 is negative, so we add to it 16, and we compute the binary representation of 10, which is 1, 0, 1, 0. Want to compute the 2's complement representation of minus 1. We add to it 16, it becomes 15, and therefore we get 1, 1, 1, 1. Suppose we want to deal with the following question. We have a binary string A, and we look at the number that A represents. And now we're interested in negating this number, that is, computing the minus of the number represented by A in 2's complement representation. What can we say about it? Well, we have the following claim. We claim that this number equals the number represented by inverting all the bits of A in 2's complement representation plus 1. Let's see an example of this claim before we prove it. Suppose that A is 0, 1, 1, 0. This is our A. We look at minus A. Well, A represents the number 6, so this is minus 6. Now let's take the bits of A and invert them. So the 0, 1, 1, 0 inverted becomes 1, 0, 0, 1. The 1, 0, 0, 1 represents in 2's complement representation minus 8 plus 1. That's the minus 8 plus 1 we see here. And there's the extra 1 from here, which the claim tells us we need to add. Minus 8 plus 1 becomes minus 6. Indeed, minus 6 on the right-hand side equals minus 6 on the left-hand side. Let's look at A, which equals 1, 0, 0, 1. It represents, in 2's complement representation, minus, this is this minus 8, this is this bit, plus 1, this is this bit. This equals 7. Now let's take the bits of A and invert them. This is 0, 1, 1, 0. This represents in 2's complement representation the number 6. To that, the claim tells us we need to add the 1. This is the 1 we have over here. We get 6 plus 1 equals 7. 7 on the right-hand side equals 7 on the left-hand side. And we see that the claim works for these two examples. So let's prove the claim. We want to prove that minus the number represented by A in 2's complement representation equals number represented in 2's complement representation by inverting all the bits of A plus 1. So let's look at this term and try to understand what it equals. The number represented by the inverted bits of A, by definition, equals minus 2 to the power of n minus 1 times the negation of the most significant bit of A plus the number represented by the inverted bits of A, the remaining inverted bits of A in binary representation. Now, recall that the negation of a bit, the inversion of a bit, simply equals 1 minus the bit. So, we can replace this thing by 1 minus the most significant bit of A. We can replace this thing by the following power series. Okay, now let us try to rearrange what is happening over here. We put a minus here for this minus, and we have here another minus over here. So we put here this minus, and we copy the 2 to the power of n minus 1, and the a n minus 1 is copied here. Okay, we have the minus over here, so this minus is the same as this minus, so we can just write here the number, the power series that corresponds to the bits of A from position n minus 2 to 0. Okay, what else do we need to add? We have here the minus 2 to the power of n minus 1 times 1, this is this fellow, and the power series with the constants 1. So this we copy here. Finally, inside the parentheses, we have the number represented by A from position n minus 1 to 0 in 2's complement representation minus, this is this minus 2 to the power of n minus 1, and this power series evaluates to 2 to the power of n minus 1 minus 1. So these two things cancel out, and we're left with the number minus the number represented by A in 2's complement representation minus 1. So if we move this 1 to here, we get that we proved the claim. Okay, we have a claim that tells us that minus the number represented by A in 2's complement representation equals the number represented by inverting the bits of A in 2's complement representation plus 1. So let's follow this recipe. Let's take the bits of A, invert them as suggested by this claim, and then add a 1. We add the 1 by employing a circuit called an incrementer. An incrementer is simply a binary adder. in which you feed the addend a bar with a representation of 1. This is all zeros and a 1. The carry in is 0. So what this adder does is it just increments. It computes 1 plus the number represented by a bar. This you get over here, and you get a carry out because this is the way an adder is built. Okay, we denote the sum output of the incrementer by b, and the carry out, this is this fellow here. And the question is whether the number represented by b in 2's complement representation indeed equals minus the number represented by a in 2's complement representation. Let's discuss this question. What does this incrementer compute? It computes the sum of the number represented by a bar in binary plus 1. But the claim tells us we wanted to compute this sum where the number represented by a bar in 2's complement representation, not in binary. So does it really help to do this increment? What do we know about this adder or this incrementer? We know that C concatenated with B in binary representation equals the number represented by a bar in binary representation plus 1. This is the functionality of this subcircuit. Well, does it help us negate A? Does it help us? Does B indeed represent minus A in 2's complements? Okay, so the suspect, if you suspect that this circuit is wrong, the suspect is Cn, right? Well, it seems that if Cn is 1, we're in trouble. So let's assume for the sake of discussion that Cn is indeed 0. So we know that if Cn is 0, then B represents in binary a bar in binary plus 1. Does this imply that B in 2's complement represent what a bar represents in 2's complement plus 1, which would mean that it equals minus A? Is it true? Consider the following example. Consider A, which is 1 in all zeros. We know that the number represented by this string is 2 to the power minus 2 to the power of n minus 1. Now let's invert the bits. The inverted bits will be 0 in all ones. Now let's do an increment. The increment will be 1 in all zeros, and the carry-out bit will be 0. So indeed, Cn is 0, as we would like to think is the innocent case. But notice that A equals B. A is 1 in all zeros, B is 1 in all zeros. So clearly B does not represent minus A, because the only number that equals its negation is 0. So this circuit is in fact wrong, even though Cn equals 0. So you may ask, is this the only example in which this circuit makes a mistake? Are there other examples in which this circuit makes a mistake? Okay, so we refer to negation as the task of computing the minus number represented by the binary string. In the case of sign magnitude, negating is very easy. You just need to flip the sign bit. In case of 1's complement representation, negating is also easy. I'll leave it as an exercise. In 2's complement representation, it turns out that you need to check whether minus A is indeed in Tn. If it isn't in Tn, then clearly you're going to make a mistake, and this is exactly what happened in this case. Yeah? And minus the number represented by A is 2 to the power of n minus 1, which is too big. It doesn't belong to Tn, and therefore we had to make a mistake. The question is whether, in all other cases, the negation circuitry that we saw in the previous slide is correct. So we need to find a proof, and we need to tell whether we fail or not when we do the computation. So we will deal with this question. But first, let's see a few properties of 2's complement representation. The first property is the sign bit. I'll leave it as an exercise to check that the number represented by A in 2's complement representation is negative, if and only if the most significant bit of A is 1. Do not be confused by this claim. It doesn't mean that the most significant bit plays the same role as the sign bit in sign magnitude. Okay? Do not be confused. So if I look, for example, at this part, it is not that A represents minus 7. In 2's complement representation, the all 1 string represents minus 1. whereas A here represents, of course, 7. Good. Now let's explain what sign extension is. Okay, we claim that duplicating the most significant bit in 2's complement representation does not affect the value that is represented by the string. This is similar to padding zeros from the left in binary representation. So, if the 2 most significant bits of A are equal, then the number represented by A from positions n to 0 equals the number represented by A from positions n-1 to 0 in 2's complement representation. Let's see an example of, before we see an example, let's see a corollary. By duplicating the most significant bit again and again and again, we get by induction on the number of repetitions of the most significant bit that the number represented by any number of repetitions of the most significant bit is the same as the original number represented by A. So for example, if you started with 1, 0, and you padded another 1, and then you padded another 1, then you padded another 1, and you end up with this type of string, they all represent the same number, which is -2. And the same thing, you could start with the 1 and start padding 1, 1, 1, 1, 1, and 1 as many times as you wish. You're always going to represent the same number in 2's complement representation, namely -1. Let's prove the claim. The proof is as follows. The number represented by A from position n to 0 in 2's complement representation by definition is written over here. You can notice that here I expanded the second most significant bit, namely A n minus 1, which has weight 2 to the power of n minus 1, whereas the most significant bit has a weight of minus 2 to the power of n. The remaining bits have a power of 2 to the I, where I is the location of the bit. Now we know that an equals an minus 1, so these two bits are equal, so we can group it together. We get minus 2 to the power of n plus 2 to the power of n minus 1 times an minus 1 plus the remaining part of the string. Now this difference becomes minus 2 to the power of n minus 1 times an minus 1, and this is exactly the definition of the number represented by A from position n minus 1 to 0 in 2's complement representation. Let's consider the following setting. I have two binary strings, A and B, and a carry-in bit C0, and my goal is to compute their sum, where A and B represent numbers in 2's complement representation. Okay, so A is n bits long, B is n bits long. I input A and B and C0 into an adder of n bits, say an RCAN, and I get an output of a sum of n bits and a carry out Cn. Now, the adder tells me that the sum of the numbers represented by A and B in binary representation plus C0 equals the number represented in binary representation by the string which is obtained by concatenating Cn with S from position n minus 1 to 0. So I know I have this nice relation between A, B, C0, Cn, and S. But this is not the sum I wanted to compute. The sum I wanted to compute is this sum. So, is it ever possible that my S, this sum string, this S represents in 2's complement representation the desired sum? How can we know if this equation actually holds, and when does it hold? The following theorem deals with exactly this situation. So we consider the situation in which we feed A, B, and C0 to an adder, to a binary adder, to obtain Cn and S, and let us even denote by Cn minus 1 the carry bit in position n minus 1 associated with this binary addition. Z is our desired sum, the sum that we want to actually compute, where everything is represented in 2's complement. Okay. Theorem tells us that if the two carry bits Cn and Cn minus 1 are equal, then the desired sum is representable by Tn, and if Z is in Tn, then the two carry bits are equal. And if Z is indeed in Tn, then Z will be represented by S in 2's complement representation. However, if these two carry bits Cn and Cn minus 1 do not equal each other, then either z is going to be too small or too big. It's not going to be in Tn, and there's no chance that z will be represented by s in 2's complement representation. Let's prove the theorem. I'll leave this example for you to work out. Okay, proof of the theorem. Let's look at our desired sum, and let's expand it. This is what A represents in 2's complement representation. So I take the most significant bit, this is its weight, and I take the remaining part of A. I do the same with B. I take its most significant bit, its weight, and the remaining part of B, and I copy C0. Now I look at these first three terms. These first three terms are actually fed into an RCA with n-1 bits. And this RCA computes the first n-1 bits of S and the carry bit Cn-1, whose weight is 2 to the power of n-1. Now I can take this Cn and put it in the parentheses. Notice I have a minus here, so I have to put a minus before the Cn-1. An-1, Bn-1, and Cn-1 are the inputs of the full adder in position n-1 of my RCA. It outputs Cn and Sn-1 and satisfies this equality. So now by rearranging, I get that the three terms here that are written in the parentheses equal 2 times Cn minus Cn-1 plus Sn-1. So I can substitute this part in the parentheses with this part. Okay? What do I conclude? Well, I have here 2 times minus 2 to the power of n-1, so that becomes minus 2 to the power of n times Cn minus Cn-1. And I have the Sn-1 with a weight of minus 2 to the power of n-1, so I could put it here with 2's complement representation, and the remaining bits of S get the same value. So this is my conclusion. Okay? The desired sum always equals this expression. Now, having reached this equality, I need to consider 3 cases. Either Cn minus Cn-1 is 0, Cn minus Cn-1 is 1, or Cn minus Cn-1 is minus 1. If Cn equals Cn-1, then this part becomes 0, and Z is indeed represented by S in 2's complement representation as desired. If Cn minus Cn-1 is 1, then Z equals minus 2 to the power of n plus the number represented by S in 2's complement representation. This number is bounded by 2 to the power of n-1 minus 1. So I get that Z is less than or equal to minus 2 to the power of n-1 minus 1. This is too small. Z is not in Tn. If Cn minus Cn-1 is minus 1, then Z equals plus 2 to the n, because I have minus 1 times minus 2 to the n, so it becomes 2 plus 2 to the n, plus a number represented by S in 2's complement representation. The number represented by S is at least minus 2 to the power of n-1, so then I get 2 to the n minus 2 to the power of n-1, which equals 2 to the power of n-1. This is too big. This is not in Tn. So Z is not in Tn in this case. So I get, if the 2 carry bits are equal, Z is represented by S. If the 2 carry bits are not equal, Z is not in Tn. It's either too small or too big. And since these are the only 3 cases, I get that if Z is in Tn, that the 2 carry bits must be equal, and Z is represented by S in 2's complement representation, and that completes the proof of the theorem. Okay, now I want to detect overflow. I have my desired sum, and I want to know whether the desired sum is in Tn or not in Tn. Overflow is 1 if Z is not in Tn and 0 otherwise. You may say that the name overflow suggests that Z is too big. Well, in fact, what it says is that it's out of range. But the literature refers to this incident in which Z is not in Tn as overflow, so we will favor tradition here. And by our theorem, we know that the overflow signal is simply the XOR of the 2 carry bits Cn and Cn-1. We want to determine the sign of the desired sum. Negative, the negative flag, is 1 if z is less than 0. It's 0 if z is greater than or 0 than 0. So we could use the brute force method. If there's no overflow, we know that S represents z, and therefore the most significant bit is the sign bit, as required. But if there is overflow, then this bit is not going to be equal to the negative signal, because a negative signal should always be correct regardless of whether there was an overflow or not. So if this difference is 1, we know that our z is way too small, and therefore negative is 1. If this difference is 1, we know that our z is way too big, and therefore the negative signal should be 0. Okay, so this is one way to compute the negative signal. Another way to compute the negative signal is simply to take the XOR of these 3 bits. Why is this correct? How do we prove this claim? To prove this claim, let's extend A and B by 1 position. So we duplicate the most significant bit of A, we duplicate the most significant of B, and we perform addition of A plus B plus C. Recall that duplicating the most significant bit does not change the value that is represented by the binary string in 2's complement representation. Now we perform the sum. We get these sum bits plus this sum bit in position n, because we are doing addition from position 0 to position n. There's also a carry out here. We don't want to worry about it now. Now, I'll leave it as an exercise that the desired sum is always in Tn plus 1, namely it's representable in 2's complement representation using n plus 1 bits. No overflow. Because there's no overflow, we know that this part represents the desired sum. So z is represented by s tilde n concatenated by s from position n minus 1 to 0 in 2's complement representation. Now the sign of z in this case is determined by the most significant bit. So the negative signal simply equals Sn tilde. But what is Sn tilde? It is an output of a full adder which is fed by these 3 bits. So Sn tilde is the XOR of An minus 1, Bn minus 1, and Cn as required. We want to design a 2's complement adder. What is a 2's complement adder? It's a combinational circuit specified as follows. We have 2 strings, n bits each, and a carry in C0. And our output is S, n bits long, and 2 flags, negative and overflow. Let Z denote the desired sum, the number represented by A in 2's complement, plus the number represented by B in 2's complement, plus C0. The functionality of the 2's complement adder should be as follows. If Z is in Tn, then S should represent Z in 2's complement representation. If Z is in Tn, then the overflow should be 0. If Z is not in Tn, the overflow should be 1. If Z is negative, the negative should be 1. If Z is not negative, the negative should be 0. We denote such a circuit by S adder N. S for signed. 2's complement signed adder. The implementation of the 2's complement signed adder is as follows. We take a binary adder, we feed it with A, B, and C0, we get Sn minus 1 and Cn. The overflow is the XOR of these 2 carry bits. Where do we get this carry bit from? Where do we get this carry bit from? Well, this carry bit is exactly this one. Where do we get Cn minus 1? Well, we need to grab it somewhere within the adder and take it to here. Okay, so for example, in a ripple carry adder, it's very explicit, and in most adder designs, you can extract Cn minus 1 from the adder and feed it to the overflow circuitry. The negative signal is simply the XOR of An minus 1, Bn minus 1, and Cn. So we need to also send Cn to here. Good. This is the description of the 2's complement signed adder. Now we want to design a 2's complement adder subtractor. This is a circuit that can either perform addition or subtraction. The input consists of 2 binary strings A and B, n bits each, and another input called subtract, which is either 0 or 1. Notice, we do not have anymore the input C0. It's gone. The output is a binary string S of n bits and two flags, negative and overflow. Define Z to be as follows. The number represented by A in 2's complement representation plus minus 1 to the power of sub times the number represented by B in 2's complement representation. Notice, if sub is 0, minus 1 to the power of 0 is 1, so this is actually addition. If sub is 1, minus 1 to the power of 1 is minus 1, so what we're doing is subtraction. So Z is either the sum or the difference between A and B. The functionality is defined as follows. If Z is in Tn, then S should represent in 2's complement representation the desired sum or difference. If Z is in Tn, the overflow is 0. If Z is not in Tn, the overflow is 1. If Z is less than 0, negative is 1. If Z is not negative, then negative should be 0. We denote such a circuit, such a combinational circuit, by add, subtract, in. How do we design this circuit? Here's an implementation of an add, subtract, in. We have a signed adder here. It is fed by A on one side, and on the other side we take B. We pass it through a bitwise XOR with sub, and we take the sub bit and we insert it as the carry-in input of the signed adder. Finally, we have a real use for this carry-in bit. The signed adder has three outputs, the string S, which denotes the sum, and the two flags, overflow and negative. And our claim is that this circuit is a correct implementation of an adder subtractor. Let us consider two cases. The first case is the case in which the subtract is 0. If the subtract is 0, then we're inputting a 0 here, and by doing a bitwise XOR with a 0, the output here equals B, and we're simply doing A plus B plus 0 in our addition, and in fact, by the correctness of the signed adder, we get the right result. So correctness holds because S adder is correct. Now let's consider the case in which the subtract bit is 1. If the subtract bit is 1, then here we're inserting a 1. We're doing a bitwise XOR with a 1. This gives us not B, the inversion of B. And here we're inputting a 1. So in fact what we're doing is we're computing A plus the inversion of the bits of B plus 1. Now, this part we know equals minus the number represented by B. Always. This is the claim on negation. So we get that we are computing A minus B. If no overflow occurs, S will represent this difference as required. If an overflow occurs, we will notice it over here, and the negative flag will always be correct regardless of whether an overflow occurred or not. Let's summarize. We discussed three ways for representing negative integers: sign magnitude, 1's complement, and 2's complement. We focused on 2's complement representation. We discussed the issue of negating the number represented by a binary string. We discussed properties of 2's complement representation, the fact that it is the modulo 2 to the power of n congruent representation to binary representation, that the most significant bit tells us whether the number is negative, and that if we extend the sign, that is, if we don't duplicate the most significant bit, we do not change the value that is represented by the binary string in 2's complement representation. We reduce a task of 2's complement addition to binary addition, and discussed how we could detect overflow and how we can determine the sign of the sum even if an overflow occurs. And finally, we presented an implementation of a circuit that performs both addition and subtraction in 2's complement representation, This is a basic part in arithmetic logic units which form a basic part of microprocessors. Thank you very much.